Hello and welcome back. In today's video, we're overclocking the Intel Core i5-12400 processor all the way up to 5.3 GHz using the ASUS ROG Maximus Z690 Extreme motherboard and EK Quantum custom loop water cooling. As I had already hinted at in my Alder Lake launch video, non-K overclocking on Alder Lake is back. However, I feel like the enthusiastic media and the hyped up overclocking community missed a big part of the story. So in this video, I set out to provide additional context and color on this topic of Alder Lake non-K overclocking. This turned out to be a very long piece, but very exciting. It was the first time in a long while that I've overclocked a non-K processor. So I had a lot of fun making this video, and I hope you have a lot of fun watching this video. The Intel Core i5-12400 processor is part of Intel's 12th generation core processor lineup. Intel Alder Lake has an all-new core design with performance hybrid architecture featuring performance cores and efficient cores. It's built on the Intel 7 process technology, formerly known as 10nm enhanced superfin. While we extensively covered the K-SKU processors on this channel already, we've said almost nothing about the non-K processors. The non-K processors include essentially all the processors that don't carry the K suffix and are, by definition, not overclockable. While the Core i7 and Core i9 Alder Lake non-K processors have E-cores, from Core i5 downwards, the processors only have the high-performance P-cores. It's important to note that they also have a completely different and much smaller H0 die. This will be important later on. The Core i5-12400 processor has 6 P-cores and a total of 12 threads. The base frequency is 2.5 GHz for the P-cores. The Turbo Boost 2.0 frequency for single core is 4.4 GHz and for all core is 4 GHz. The processor base power is 65 watt and the maximum turbo power is 117 watt. In this video, we will cover 4 different overclocking strategies. First, we enable AVX512, MCE and XMP. Second, we overclock using the conventional BCLK method. Third, we use non-K BCLK overclocking and a fixed CPU ratio. Lastly, we use non-K BCLK overclocking and a dynamic turbo CPU ratio. However, before we jump into the overclocking, let's have a quick look at the hardware and the benchmarks we'll be using in this guide. Along with the Intel Core i5-12400 processor and ASUS ROG Maximus Z690 Extreme motherboard, in this guide we will be using a pair of 16GB DDR5 6200 Hynix memory sticks, an RTX 2080 Ti graphics card, a 512GB M.2 NVMe SSD, a Seasonic Prime 850W Platinum power supply, the Elmo Labs EasyFan controller, the Elmo Labs power measurement device, the Elmo Labs EVC2, and EK Quantum water cooling. All this is mounted on top of our favorite Open Bench Table V2. The cost of the components should be around $4,927. I know the motherboard is not a price match nor a segment match for the Core i5-12400 processor. The primary purpose of this video is to show you how non-K overclocking works, not really to argue whether it makes sense from a value for money perspective, although we'll touch a little bit on that later in the video. I explain how I use the Elmo Labs products in SkatterBencher number 34. By connecting the EFC and PMD to the EVC2 device, I monitor the ambient temperature, water temperature, fan duty cycle, and CPU input power. I include these measurements in my Prime 95 stability test results. I also use the Elmo Labs EFC to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. I use this configuration for all overclocking strategies. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start any overclocking, we first have to check the system performance at stock settings. Please note that the ASUS ROG Maximus Z690 Extreme motherboard unlocks MCE and AVX512 out of the box. So if you want to check the performance at default settings, you first have to go into the BIOS and enter the Extreme Tweaker menu, Set ASUS multi-core enhancement to disabled, enforce all limits. Enter the AVX related controls submenu. Set AVX512 to disabled. Then save and exit the BIOS. Here's the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 3140 MHz with 0.909 volts. The average CPU temperature is 45 degrees Celsius. The ambient and water temperature is 23.2 and 29 degrees Celsius. The average CPU package power is 65 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 3500 MHz with 0.956 volts. The average CPU temperature is 47 degrees Celsius. The ambient and water temperature is 23.2 and 29.3 degrees Celsius. The average CPU package power is 65 watts. Alright, let's get into the overclocking now. But before you do that, make sure to locate the 3 following buttons: Save Boot button, Read Dry button, and Clear CMOS button. In our first overclocking strategy, we simply try to take advantage of enabling AVX512, enabling ASUS multi-core enhancement, and enabling Intel Extreme Memory Profile. One of the most interesting topics of the Alder Lake launch was the support for AVX512 instructions. While Intel had communicated that Alder Lake does not officially support AVX512, they had mentioned P-core support for the instruction set in technical documentation. As became evident when Alder Lake launched, while official support was indeed missing, you can still enable AVX512 through BIOS. But there's a caveat. As only the P-cores support the instruction set, you must disable the E-cores to enable AVX512. Of course, that would seriously hamper the multi-core performance of, for example, the 12900K. Fortunately, our Core i5-12400 processor doesn't have E-cores, so enabling AVX512 is pretty much the definition of free performance. However, as several media have reported, Intel has disabled the AVX512 capability through updated microcode. On newer public BIOSes with the 0x18 microcode, you'll no longer find AVX512 support. That said, enthusiasts have figured out a way to inject the older microcode into new BIOSes for those who want AVX512 support. As we're still on an older BIOS that has the 0x15 microcode, we can still benefit from enabling AVX512. ASUS multi-core enhancement is a single BIOS option that allows us to fully unleash the Intel Turbo Boost 2.0 algorithm. Effectively, by enabling MCE, we tell the processor to run at full power and full performance for an indefinite amount of time. Intel Turbo Boost 2.0 technology allows the processor cores to run faster than the base operating frequency if the processor is operating below rated power, temperature, and current specification limits. The Turbo Boost algorithm works according to a proprietary EWMA formula. EWMA stands for Exponentially Weighted Moving Average. There are 3 parameters to consider: PL1, PL2, and tau. If the average power consumed is higher than PL1, the CPU will reduce the CPU frequency. A significant change from previous architectures is that Alder Lake is moving away from the TDP concept and instead has 2 power-related specifications: processor base power, formerly the TDP and PL1, and maximum turbo power, formerly PL2. This new format aligns with how the processor frequency has base frequency and a maximum turbo frequency. Intel Extreme Memory Profile is an Intel technology that lets you automatically overclock your system memory. It is an extension of the standard JEDEC specification that allows memory vendors to program different memory settings like voltage or timings or frequency onto the memory sticks. Intel Extreme Memory Profile 3.0 is a new XMP standard for DDR5 memory. It is based mainly on the XMP 2.0 standard for DDR4, but has additional functionality. The XMP 3.0 standard is designed with 6 sections. One global section describes the generic data used across the profiles. The other 5 sections are designed for 5 profiles respectively. If you want to learn more about XMP 3.0, then feel free to check out my launch video on Alder Lake. Upon entering the BIOS, enter the Extreme Tweaker menu. Set AI Overclock Tuner to XMP1. Set ASUS Multicore Enhancement to Enabled, remove all limits. Enter the AVX Related Controls submenu. Set AVX512 to Enabled. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. As expected, we see the most extensive performance difference in multi-threaded applications utilizing AVX instructions, as these were previously constrained by the maximum long-term power of 65 watt. We see up to a 20.85% performance increase in AI benchmark. When running Prime 95 small FFTs with AVX enabled, the average CPU peak core clock is 4000 MHz with 1.057 volts. The average CPU temperature is 64 degrees Celsius. The ambient and water temperature is 23.5 and 31.8 degrees Celsius. The average CPU package power is 110 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU peak core clock is 4000 MHz with 1.046 volts. The average CPU temperature is 57 degrees Celsius. The ambient and water temperature is 23.5 and 30.8 degrees Celsius. The average CPU package power is 95.9 watts. Now let's move on to the actual overclocking. I presume that anyone who's watching this channel is already familiar with how Intel segments their CPUs and their chipsets. In short, you'll need a specific CPU and a specific chipset that is enabled for overclocking to do overclocking. On the CPU side, you'll need a K or an X or any of the variants. On the chipset side, you'll need a Z motherboard or an X motherboard to enable the overclocking as well. The main difference between these unlocked overclockable parts and the locked non-overclockable parts is that you don't have access to any of the ratios to actually do the overclocking. Furthermore, also these locked processors don't allow for any BCLK overclocking. It has a hard limit. And the hard limit is set at 103 MHz. So effectively on locked parts, you are limited to up to 3% more performance if you try overclocking. Intel's history with locked and unlocked parts goes back a long time. Let's take a trip down memory lane. To give a processor its operating frequency, you need two things, a reference clock and a multiplier. For most modern CPUs, there's a crystal on the motherboard used by either the CPU or chipset to produce an internal reference clock of 100 MHz. This 100 MHz is then multiplied using a PLL to achieve the final operating frequency. To lock a processor to a specific frequency, you, therefore, need to lock three parts: the crystal, the reference clock, and the multiplier. Intel's story of locking processors for enthusiasts and overclockers begins in mid-1998. Leading up to the crackdown on overclocking, Intel was upset that people would buy a lower spec part and then overclock it to get higher performance. There were two main reasons why Intel was upset. First, at the time, the operating frequency was a key selling point of the CPU, as it was the main differentiator of compute performance. For every additional 33 MHz, Intel could charge a significant premium. Therefore, there was a direct financial impact when customers buy a lower rated part and run it at the frequency of the most expensive part. Of course, today's situation is very different, as there is a wide variety of performance differentiating features such as core count, integrated graphics, and memory speed support. 2. People set up businesses selling remarked processors. Remarked processors are lower spec parts sold as higher spec parts. One could argue that this is the same as pre-bin CPUs, though it's not quite the same. A remarked CPU would be advertised and sold as a different product out of the box. In contrast, a pre-bin CPU is still advertised and sold as the original product, but with a specific overclocking capability. There was a significant financial incentive to remark processors. A 350nm Pentium 2 233 Clamate processor was listed at $636, while its bigger brother, the Pentium 2 300, was listed at a whopping $1,981. However, things changed when the 250nm Deschutes Pentium 2 came to market. While early and engineering samples had an unlocked multiplier, most parts were multiplier locked. For overclockers, that left only the reference clock to overclock the CPU. The "soon overclocking will end" meme has been around for a long time, as proven by the opening lines of a 1998 Tom's Hardware article. The main reason for the desperate feeling among PC enthusiasts was that Intel would not only multiplier lock but also bus lock its processors. Despite the great fears in 1998, it took Intel a very long time to put constraints on the reference clock overclocking. That said, the Pentium 3 processors were all multiplier locked. This enabled a great point of differentiation for motherboard vendors, as the ability to increase the reference clock was now a key selling point for PC enthusiasts. The reference clock became one of the main battlegrounds for competitive overclocking. By 2010, the highest reference clock frequency had increased from less than 200 MHz of the Pentium 3 Slot 1 to over 700 MHz. Incredibly, the world record of 750 MHz, set on October 30th, 2009 by Indonesian overclocker Benny Lodewijk, stood for more than a decade. Only last year, a Chinese overclocker by the name of WYTIWX beat the record. The highest ever reference clock frequency now stands at 766.1 MHz. Overclocking the reference clock not only helped to increase the CPU frequency, but it also provided a significant performance uplift for the front-side bus. For the younger viewers among you, back in the old days, a motherboard would have two chips, the North Bridge and the South Bridge. The North Bridge would host not only the memory controller hub with access to the system memory, but, in some cases, also links to high-speed graphics buses like AGP or PCI Express. The South Bridge contained all connections to I/O like low-speed PCIe, SATA, USB, and so on. The North Bridge and the CPU would connect with a high-speed frontside bus. As this bus transfers data between memory or graphics and the CPU core, it's easy to understand that a higher frequency would undoubtedly provide much higher performance. For overclockers, a high frontside bus was one of the primary ways to get more performance, alongside, of course, a higher CPU frequency and higher system memory frequency. This is relevant to our story of locking the CPUs, and we'll get back to that later. But first, let's return to the year 2003. 2003 was a critical year for Intel for several reasons. One, Intel's NetBurst microarchitecture, which set out to achieve clock frequencies of up to 10 GHz by 2011, turned out to be a wrong design choice as it ran into physical limitations like heat and power. As a result, Intel had to abandon the development of Tejas and Jayhawk products. 2, the industry experienced a paradigm shift away from the frequency race and onto the multi-core race to chase performance improvements. 3, AMD launched the Athlon 64, the very first consumer 64-bit processor and the first processor with an integrated memory controller. 4, Intel launched their very first Extreme Edition processor to counter the Athlon 64, which media generally saw as a marketing tactic to divert attention away from the significant strides forwards of their competitor. In other words, 2003 was not a great year. Intel's first Extreme Edition processor, the Pentium 4 Extreme Edition 3.2 GHz, launched on November 3, 2003, about a week before AMD unveiled their first Athlon 64 processor. The Extreme Edition is a 169 million transistor Pentium 4 running at 3.2 GHz with hyper-threading support. It also supports a 2 MB on-die L3 cache in addition to the standard 512 KB on-die L2 cache. Anantech informed Intel that a processor would be truly worthy of the Extreme Edition name if its multiplier were unlocked for overclocking. It wasn't until the Pentium Extreme Edition 840, released on May 1, 2005, that Intel would fully unlock the CPU multiplier. It was the first time in almost 5 years that enthusiasts could overclock without changing the reference clock frequency. Intel would provide their customers with locked regular processors and unlocked Extreme Edition processors going forward. The last Extreme Edition release is the Intel Core i9 10980 XE Extreme Edition Cascade Lake processor for X299 motherboards launched on November 25, 2019. Unlocking the CPU ratio multiplier offered Intel three key benefits. First, it allows Intel to claim feature parity with AMD's FX product line, which offered an unlocked multiplier on the first Athlon 64 FX51 processor launched in September 2003. Second, it helps justify charging a significant premium for the Extreme Edition processor, as unlocked multipliers offer added value over locked processors. Third, it enables Intel to fight at the top of the performance leaderboards, whether in media reviews or overclocking benchmark records. It would have made a fantastic business model if the Extreme Edition CPUs were the perennial leaderboard top spot holder. But Intel had a problem. Reference clock overclocking. By the time Intel started rolling out its unlocked Extreme Edition processors in 2003, motherboards with the contemporary 865p chipset could run the reference clock frequency well above 300 MHz and thus offer more than 50% overclocking headroom. When Conroe came around in 2006, it was clear. The overclocking headroom of the reference clock and frontside bus frequency was more than enough to overcome the locked multiplier limitation. As a result, enthusiasts were buying the cheaper processors and would very easily overclock them to match or exceed the performance of the Extreme Edition processor. Even when it comes to the liquid nitrogen overclocking leaderboards, the Extreme Edition wasn't necessarily the way to go. The fastest Conroe or Kensfield processor is still a 5.9 GHz Core 2 Duo E6850, and the fastest Wolfdale or Yorkfield processor is a 6.9 GHz Core 2 Duo E8600. By the end of the LGA 775 era, the reference clock overclocking capabilities exceeded 700 MHz, far above the default frequency of 333 MHz, and offering more than enough headroom for any processor. When Nehalem came around in November 2008, things started to move slowly away from reference clock overclocking, or we should call it base clock overclocking now, as per Intel terminology. The base clock was significantly reduced to 133 MHz, and the frontside bus technology made way for Intel's quick path interconnect technology. Most importantly, Nehalem introduced two important technologies: turbo mode and the power control unit. Turbo mode is a technology that allows the CPU cores to run faster than the base frequency if there is sufficient power, thermal and current headroom. The power control unit is a 1 million plus transistor on-die memory controller managing the CPU cores. It has its own firmware and uses inputs like temperature, current, power and operating system requests to manage the CPU core frequency and power. Long story short, the PCU controls the CPU. Together, these two parts would play a pivotal role in the upcoming crackdown on overclocking. We'll get back to that story, but let's first finish up on the base clock overclocking. The Nehalem platform for desktop was split into two distinct segments: high-end desktop with Bloomfield and mainstream desktop with Linfield. While Bloomfield processors generally had a base clock hard wall at about 220 MHz, which could be overcome by increasing the PCIe frequency, Linfield suffered less from a BCLK overclocking limitation. While the maximum frequency dropped significantly from the record highs of over 750 MHz to below 300 MHz, the base clock frequency range was still more than sufficient. There is perhaps no better example than HWBot's W'1024M leaderboard ranking, which has a mix of Core i7 Extreme Edition, Xeon, and the cheapest Bloomfield topping the charts. The BCLK overclocking range improved with Nehalem's successor, Westmere, which had Gulftown for the high-end desktop and Clarkdale for the mainstream desktop. While the Gulftown 980X and 990X were the way to go for multi-threaded benchmarks, a Core i7 970 could still be competitive given your motherboard would provide sufficient base clock headroom. However, when it comes to raw overclocking capability and maximum frequency, the cheapest Core i5 and Core i3 Clarkdale processors would be right up there above 7 GHz with the most expensive Core i7s, thanks to the BCLK overclocking headroom. But then came Sandy Bridge, and everything came to a screeching halt. No more BCLK overclocking. Page 5 of Anantic's Sandy Bridge preview article is titled Overclocking Controversy and accurately captures the sentiment of the PC enthusiast community. 3 things had changed since Intel's decision to lock the CPU ratio. First, through the Extreme Editions, Intel had begun experimenting with multiplier unlocked processors and had been able to evaluate the impact on its business from various angles: the marketing benefit, the financial benefit, and impact on return rates, for example. Second, starting from Penryn and later adopted in Nehalem with Turbo Boost technology, Intel now has a way to exploit the overclocking headroom out of the box. Third, with the integration of the power control unit, Intel had a much tighter grip on everything related to overclocking. While Nehalem still relied on an external clock generator provided by the motherboard, Intel integrated the clock generator for Sandy Bridge in the PCH. Remember this last point, as it will play an important role once we finally get to Alder Lake non-K overclocking, and I promise we'll get there. As it would turn out, the BCLK overclocking capabilities of Sandy Bridge processors were extremely limited, as it was tied to the DMI and PCIe clocks. The best BCLK overclock is still only 111.86 MHz, not even 12% higher than the base frequency of 100 MHz. So just like Tom's Hardware Guide had predicted in 1998, overclocking is dead, right? Not quite. Intel had made several important decisions that would ensure overclocking was alive and well. Since 2009, the company had experimented with much more affordable multiplier unlocked K processors. The first K processor was the Pentium E6500K, a multiplier unlocked Wolfdale processor launched exclusively in China. Following what I assume had been a successful experiment, in May 2010, Intel introduced the Core i7-875K Linfield and Core i5-655K Clarkdale processors. While the Core i5 model was priced $40 higher than its locked counterpart, surprisingly, the Core i7 model was priced significantly lower than its locked counterpart. With the launch of Sandy Bridge, Intel introduced the K business model to the broader market, a slightly higher priced but fully unlocked model alongside a locked counterpart. So overclocking was safe, right? Well, sort of. Sandy Bridge's overclocking controversy didn't end with just the limited base clock overclocking. There was actually a lot of problems with Sandy Bridge overclocking. First, Intel forced the customer to choose between overclocking or using integrated graphics. The P67 chipset would support CPU overclocking, but wouldn't allow for the integrated graphics and its very useful quick sync acceleration. The H67 chipset would enable full use of the integrated graphics, but disabled the overclocking capability. So if you bought a Core i7-2600K, you had to choose OC or IGP. Fortunately, Intel swiftly addressed this controversy by introducing the very first Z chipset, the Z68. Second, CPU ratio overclocking did not go very smoothly at all. Most CPUs would initially be limited to the 53x ratio. Only after introducing an option called internal PLL over voltage override, you could increase the CPU ratio beyond 53x. Third, the CPU ratio range was minimal, as it would only go up to 57x. That was too limited for extreme overclockers, as plenty of Sandy Bridge CPUs would overclock well past 5.9 GHz. Lastly, memory overclocking was also incredibly limited, as Sandy Bridge offered memory ratios up to only DDR3 2133. As a result, the highest memory frequency ever achieved on Sandy Bridge processors is around DDR3 2368, and that's significantly lower than the DDR3 3200 plus its mainstream predecessor Linfield was capable of. All things considered, the K-SKU saved overclocking on the mainstream platform, but it was indeed severely limited. Intel had made an additional decision to unlock every processor on its high-end desktop platform. Unlocking also meant the creation of BCLK multipliers, which allowed you to run at 100, 133, 166, or 250 MHz base clock frequency. But for mainstream non-K processors, the overclocking fun was over. For Sandy Bridge, Ivy Bridge, and Haswell, the maximum base clock frequency for non-K locked processors is limited to around 111 MHz. Whereas for unlocked K processors, the maximum BCLK frequency is much higher. Before I get back to the Core i5-12400 processor, which we are trying to overclock in this guide at some point, I need to mention Skylake, as there are striking parallels with non-K overclocking on Alder Lake. Skylake introduced a new feature called BCLK Governor, an integrated circuit that calculates the base clock frequency at real time and will issue a machine check error if the BCLK is higher than the allowed limit. Importantly, BCLK calculation doesn't rely on using the integrated clock controller from the PCH, as it works with external clocks as well. External clocks? Yes, another key new feature on Skylake was the re-enabling of full-range, fine-grained BCLK overclocking. For this purpose, motherboard vendors could add an external clock generator to the motherboard, bypass the internal clock generator, and use it as the base clock frequency. The result was quite spectacular, as the BCLK could overclock to over 550 MHz, the highest since the Core 2 days. With this kind of BCLK overclocking range, Intel definitely needed its BCLK governor to both monitor the BCLK frequency in real time and make sure that the CPU stopped working once it exceeded a hard-coded limit. On December 2nd, 2015, almost 4 months after the launch of Intel's 6th generation processors and brand new CPU architecture Skylake, the overclocking world woke up to a Core i3-16420 processor with an overclocked BCLK frequency of 120 MHz. As we'd learn in the days and weeks to come, Supermicro had found a way to work around the power control unit, which is responsible for managing the CPU's power consumption, performance, as well as housing the BCLK governor. With the PCU out of the way, there was no means to check the BCLK frequency and throw an error, so non-K overclocking was back. Unfortunately, disabling the PCU came with a couple of significant drawbacks. Despite the drawbacks, some motherboard vendors went all in on promoting non-K overclocking. Most notably, ASRock had set up an entire marketing campaign for its SkyOC feature. As expected, Intel pressured motherboard partners to remove non-K overclocking support, and most motherboard partners withdrew official support. That said, extreme overclockers and enthusiasts could still find and use the old BIOSes with non-K OC support. The BCLK governor measures the real-time BCLK frequency and checks it against a hard-coded limitation. Since Skylake, the BCLK limitation is 103 MHz. So while the highest non-K BCLK frequency for Skylake was 213 MHz, ever since Skylake, the non-K maximum BCLK frequency is about 103 MHz. And here's where we finally pick up our overclocking guide. In our second overclocking strategy, we overclocked the 12400 processor with all the traditional overclocking restrictions in place. So we set the BCLK to 102.9 MHz, enable AVX512 MCE and XMP, and then check where we are at with the performance. Upon entering the BIOS, enter the Extreme Tweaker menu. Set AI Overclock Tuner to XMP1. Set BCLK frequency to 102.9. Set ASUS Multi-Core Enhancement to Enabled, remove all limits. Enter the AVX related controls submenu. Set AVX512 to Enabled. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Up until this point in the video, we've used performance tuning options that should be available on any Intel Z690 motherboard. The performance improvement is therefore quite impressive. Even with a small bump in base clock frequency and enabling AVX512, MCE and XMP, we're seeing the single-threaded performance increase up to 10% in 3DMark CPU profile and a multi-threaded performance increase of up to 25.25% in AI benchmark. When running Prime 95 small FFTs with AVX enabled, The average CPU peak core clock is 4013 MHz with 1.039 volts. The average CPU temperature is 61 degrees Celsius. The ambient and water temperature is 22.7 and 30.9 degrees Celsius. The average CPU package power is 103.2 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU peak core clock is 4013 MHz with 1.021 volts. The average CPU temperature is 52 degrees Celsius. The ambient and water temperature is 22.5 and 30 degrees Celsius. The average CPU package power is 90 watts. In our third overclocking strategy, we finally get to overclock our non-K Alder Lake processor. But in order for me to explain how to do it, I have to explain a little bit on how Intel enables overclocking on their K CPUs. Let's pick up the story where we left it at Nehalem. As I already mentioned, the integrated power control unit was a key innovation of the Nehalem processor as it provided Intel control over the CPU's power management. Via its integrated microcontroller, Intel could set the power and performance rules of its processor, govern it, and if necessary, even change its behavior at a later stage through BIOS updates. With Sandy Bridge, Intel also added an integrated clock generator and essentially cut off any external control over the base clock frequency. Overclocking control was now almost entirely under Intel's control. While this tight control wasn't really a problem for Intel as a whole, an internal group of enthusiasts and overclockers did realize that actions had to be taken if not only overclocking was to be maintained, but also enhanced in future platforms. In a 2013 interview, Mike Moen from Intel explained the origins and the purpose of this overclocking workgroup.
I have a couple jobs at Intel. One, I'm the lead engineer for high-end desktop and enthusiast platforms. The thing I focus on a lot is Extreme Edition processors, K-SKU processors. And so because of that, the other thing that I do is I focus a lot on overclocking. So I run an overclocking workgroup at Intel. I started back actually with Nehalem, so 2007, 2008 timeframe, and one of the VPs at the time said, hey, let's see how fast this thing can go, and that sounded kind of fun to me actually, so I just got in the lab with a couple of the performance architects and we started fiddling with things and got some great results, and it has kind of just continued to roll on from there. Well, one, I think the most significant thing we try to do is we try to be a community of users within Intel, right? We're all doing this because we love what we do. We love the architecture. We love making things go fast. And so we try to look at each platform that comes along and we try to figure out, you know, if this is the way that an overclocker is going to use it. We try to figure out, given the level of integration that is going on with each platform, how we can leverage that, how we can expose the right knobs to allow an overclocker or a performance tuner to be able to do neat things with the platform. Yeah, so, you know, while we don't, you know, per se absolutely engineer for the overclocking regime, we're engineering for a very broad range of applications and usages. But the thing that we want to make sure and do is that the logic that is designed in isn't going to be an impediment to the overclocking experience. So, you know, physics is going to be your limiter, not the logic. You know, I think that, you know, this is where I say that I work with a lot of really smart people, and these guys are designing some really innovative circuit solutions, and one thing that they don't always know is just how people are going to use them. And so one thing that we do is we actually connect sometimes this community of users and what they're doing with it. We connect them with the architects and the designers, and they're like, oh, that's really cool. And suddenly they can, because naturally, you know, being an engineer, being inquisitive, they're going to say, you know, why don't you show me what that does down there, right? And when we say, well, this is what it does, and it sure would be nice if it did something different, right? Sometimes we get them to jump in and say, okay, let's try to figure out how to fix it. So, and I think that's just kind of the natural thing of an engineer that loves to see just what their design really can do. They want to see the limits, just like, you know, the people that are doing overclocking out there, they want to see the limits. There's not that much of a difference sometimes.
While Mike has since left Intel, his successor Dan Raglan now heads the Intel Overclocking Lab. He and his team continue to push the overclocking agenda within the organization. For those who want to get to know Dan, both Intel and TechTechPotato have excellent interviews on their respective YouTube channels. Where Nehalem would introduce features that would end up severely restricting overclocking on Intel platforms, Haswell perhaps introduced the most consequential feature for overclocking that enthusiasts have never heard about: the OC mailbox. The OC mailbox is a model-specific register, or MSR, interface which communicates directly with the CPU power control unit. It is designed to program overclocking and overvolting parameters to the CPU. Over the years, the OC mailbox has replaced many legacy overclocking programming functions and significantly expanded its scope. From the business perspective, Intel uses the OC mailbox in two main ways. One, to increase value for enthusiast K, SKU, and Z chipset customers by enhancing and expanding overclocking and performance tuning functionality. Two, to gatekeep and restrict overclocking for non-K and non-Z products. Therefore, in theory, the OC mailbox should be locked unless you have a K or an X CPU and a Z or an X motherboard. This has a significant impact on the overclocking experience of non-K processors, as it means no voltage offset or override, no turbo ratio control beyond the default maximum limit, no per core ratio limit, no VF points, no BCLK aware adaptive voltage, no thermal velocity boost functions or OCTVB, and no AVX offsets. To the untrained eye, it may seem that there's nothing special about the unlocked parts, but once you know the tremendous value created through the efforts of expanding the OC mailbox, you start to appreciate the work Intel's OC Lab team is doing to enable overclocking. Furthermore, you can understand why it makes more than sense for Intel to charge a premium for these advanced features. Note that access to the OC mailbox is entirely up to Intel. They can fully unlock it for certain processors, they can partially unlock it, or they can just fully lock it down as well. It's really up to them to decide. Also note that enabling non-K overclocking for Alder Lake processors does not grant you access to the OC mailbox. All the OC mailbox restrictions for non-K Alder Lake processors are still in place, even after unlocking the BCLK. So let's come to the point of this video. With all these restrictions in place, how on earth is it possible that we can do non-K overclocking on Alder Lake? In a previous segment, I already talked about the BCLK governor. This is a feature introduced on Skylake which had one purpose: prevent the locked CPUs from going over 103 MHz BCLK. The BCLK governor monitors both the internal and external clock generator. Due to an apparent oversight, the BCLK governor does not function correctly on a specific older pre-release version of the CPU microcode 0x9. The BCLK governor works correctly for the integrated clock generator, but not for the external clock generator. Using this older microcode in combination with an external clock generator means you can increase the base clock frequency on a locked non-overclockable part beyond the artificial limitation of 103 MHz. We can only speculate as to why that oversight happened. One theory is that it has something to do with the fundamental change in clocking structure on Alder Lake. Since integrating the clock generator on Sandy Bridge, it's always been the PCH that generates the 100 MHz BCLK frequency. That was the case until Rocket Lake. However, first on Tiger Lake and now also on Alder Lake, the BCLK is added on the CPU die. The 38.4 MHz crystal still connects to the PCH, but instead of driving a 100 MHz clock to the CPU, the PCH now just forwards that 38.4 MHz clock to the CPU BCLK PLL. The CPU, in turn, generates its 100 MHz reference clock. This fundamental change in clocking structure may explain why the oversight occurred. Obviously, Intel wouldn't want the non-K parts to be overclocked using unsupported methods. I don't quite believe it's only because of financial reasons. I think it's primarily because of safety reasons. Intel doesn't want a third party to be able to make your system unstable using this unsupported method. Anyway, Considering that this exploit or this oversight is not present in later microcodes, I don't think Intel will come down too harshly on this non-K overclocking thing. Intel can encourage motherboard partners to ship new BIOSes without this older microcode, or could even enforce updating the CPU microcode via a Windows update as it did for the unlocked Pentium G3258 Anniversary Edition and non-Z motherboards. Motherboard vendors have a couple of ways to support non-K overclocking. First, they can provide specific BIOS releases with microcode 0x9 to end users. Second, they can release BIOSes with both microcodes and allow users to choose which microcode to load. That's how it works on the ASUS ROG Maximus Z690 Extreme motherboard. By enabling the Unlock BCLK option, the BIOS will load the 0x9 microcode. If this feature is disabled, it will load the latest microcode. That's 0x15 on my 0801 BIOS. So in summary, on microcode 0x9, the BCLK governor doesn't work properly, as in it doesn't monitor the external clock generator. This gives us access to BCLK overclocking, essentially unmonitored BCLK overclocking. While we have access to the BCLK, it doesn't mean that we have access to any of the advanced tools available in the OC mailbox. So while we can overclock, we still have a lot of restrictions that will prevent us from doing it very easily for a daily system. In order to understand where are our opportunities and our challenges with Alder Lake non-K overclocking, let's have a look at the Alder Lake voltage and frequency topology. The clocking of Alder Lake is much more similar to Tiger Lake than it is to Rocket Lake, as it inherits the CPU internal clock generator from Tiger Lake. The standard Alder Lake platform has a 38.4 MHz crystal as reference clock to the PCH. The PCH will then generate 3 clocks. 38.4 MHz reference clock for the CPU internal clock generator, 100 MHz PCI BCLK for PCIe, DMI and I/O, and 24 MHz frequency for TSC, display and ISVIT controller. The CPU internal clock generator then generates the 100 MHz base clock frequency used for all parts inside the CPU. Just like Rocket Lake, it is possible to bypass the internal clock generator and use an external clock generator to feed the 100 MHz BCLK to the CPU. Whichever way you get the 100 MHz BCLK, this clock is multiplied with specific ratios for each of the different parts inside the CPU. When we overclock using the base clock frequency, we affect all the parts that are driven by that frequency. So I think it's evident for anyone who's watching that not having access to the ratios higher than default on non-K processors is going to be a significant hassle. While Alder Lake clocking resembles Tiger Lake a lot more than Rocket Lake, in the voltage department it's the other way around. Alder Lake transitions away from using fiber for the cores, ring and integrated graphics compared to Tiger Lake. Instead, Alder Lake uses powered gates. However, unlike Rocket Lake, some parts of the Alder Lake CPU are powered by fiber. If we only consider the Alder Lake CPU and disregard the chipset, there are 7 different voltage inputs. First, the easiest one, VCC GT. This voltage powers the GT or integrated graphics, including the slice, unslice and display block. It supports both override and adaptive voltage mode. Second, VCC IA. IA stands for Intel Architecture and is the collective term for all Intel CPU cores. Therefore, logically, the VCC IA powers both the P cores and, if present, E cores. It also powers the ring, including the last level cache and cache boxes. All parts will run the same voltage as this is a single rail. VCC IA supports both override and adaptive voltage mode. Third, VCC in aux. Here's where the voltage gets a little bit more complicated than Rocket Lake. VCC in is the input voltage for the fully integrated voltage regulators. The fibers power many parts inside the CPU, including the E-core L2 cache, Uncore, VCC SA, and so on. To understand the limitations of non-K overclocking, you also have to know how Intel CPUs manage these voltage rails. Let's focus on the VCC IA voltage rail. The VCC IA rail is powered by an external VRM which connects to the power control unit to power the P cores, E cores, and ring. The power control unit allows 2 modes of operation, adaptive mode, and override mode. In adaptive mode, the CPU issues VID voltage requests to the VRM according to the factory-fused voltage frequency curves and power management. You can also add a voltage offset to whatever VID voltage the CPU requests. In override mode, the CPU uses a fixed voltage for all scenarios. It will still issue VID requests to the VRM controller, but the VRM controller can either follow this request or send whatever voltage it wants. That is how manual voltage configuration from the BIOS typically works. You configure the VRM controller rather than the CPU voltage request. The end user can control voltage rails using the OC mailbox functionality. While most of the OC mailbox functions are not available on my non-K Alder Lake processor, control over the VCC IA is present. I didn't check the VCC GT. Also surprisingly is that on my system at least, I can also control the VCC SA. It is surprising because there are reports of other people trying non-K overclocking who cannot change the VCC SA voltage. Furthermore, since the VCC SA voltage is not powered by a separate voltage regulator, but instead is powered by the 5er, it should technically be entirely unavailable for non-K overclocking. At the moment of filming, I still don't know why it works on my system and it doesn't work on other people's system. Now that we understand the limitations of Alder Lake non-K overclocking, let's get to work. In this overclocking strategy, we will approach overclocking from a traditional perspective. So we'll use a fixed CPU ratio and a fixed CPU voltage. Obviously, we'll be using BCLK overclocking. We'll increase the BCLK frequency. That will increase the frequency of the domains that are driven by this BCLK frequency as well. While we don't have access to ratios higher than the default maximum, we do have access to the ratios lower than the default maximum. So we'll be using those lower ratios to tune for stabilities. We'll reduce those and hopefully we get some stability. In terms of the voltage side, we're also in luck. So we have access to the normal tools for controlling the CPU voltage. In this case, we'll be using a fixed CPU voltage, so we'll set the VCCIA voltage rail in override mode. Upon entering the BIOS, enter the Extreme Tweaker menu. Set AI Overclock Tuner to XMP1. Set BCLK frequency to 122.5. Set ASUS Multicore Enhancement to Enabled, remove all limits. Set DRAM frequency to DDR5 6207 MHz. Set Performance Core Ratio to sync all cores. Set one core ratio limit to 40. Enter the AVX related controls submenu. Set AVX512 to Enabled. Leave the AVX related controls submenu. Enter the Digi plus VRM submenu. Set CPU load line calibration to level 8. Leave the Digi plus VRM submenu. Enter the internal CPU power management submenu. Set regulate frequency by above threshold to disabled. Leave the internal CPU power management submenu. Enter the Tweaker's Paradise submenu. Set unlock BCLK OC to enabled. Leave the Tweaker's Paradise submenu. Set max CPU cache ratio to 40. Set CPU core cache voltage to manual mode. Set CPU core voltage override to 1.175. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. There's not much to say about these results. Clearly, increasing the clock frequency from an all-core base of 4 GHz to 4.9 GHz will positively impact the performance. We see performance improvements across the board with a maximum gain of plus 44.26% in AI benchmark. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4900 MHz with 1.18 volts. The average CPU temperature is 93 degrees Celsius. The ambient and water temperature is 23.7 and 33.5 degrees Celsius. The average CPU package power is 156.7 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 4900 MHz with 1.18 volts. The average CPU temperature is 82 degrees Celsius. The ambient and water temperature is 23.9 and 33 degrees Celsius. The average CPU package power is 139.4 watts. In our fourth and final overclocking strategy, we will use a modern approach to overclocking. That means we'll be using dynamic turbo ratios and we'll be using dynamic adaptive voltage mode. Generally speaking, there are two ways to configure a CPU ratio on Intel platforms: sync all cores and by-core usage. Sync all cores sets one ratio that is applied to all cores. This is very much the traditional way of overclocking and our previous overclocking strategy approach. By-core usage allows us to configure the overclock for different scenarios ranging from one active core to all active cores. That enables us to run some cores significantly faster than others when the conditions are right. Intel's default Turbo Boost 2.0 configuration works precisely like this. The Core i5-12400 default configuration allows for up to 4.4 GHz when 2 cores are active, up to 4.2 GHz when 4 cores are active, and up to 4 GHz when all cores are active. The main benefit of using by-core usage CPU ratios is that we can extract a lot more performance when fewer than all cores are active. The VCC-IA voltage rail is a single rail that provides voltage to the CPU cores and the ring. Since it's a single rail, it means that the voltage for those two parts will be the same. We can configure the voltage both in adaptive mode and override mode. Adaptive mode is the standard mode of operation. In adaptive mode, the VF curve used is generated automatically by the CPU and covers the CPU ratios from the lowest supported ratio to the default maximum turbo ratio. In the case of the 12400, that's from 8x to 44x. VF curve stands for voltage frequency curve, and it's essentially a line that describes the relationship between an operating frequency and its required operating voltage. Using adaptive voltage offset, the entire VF curve can be offset by up to 500 mV in both directions. Also, since Alder Lake, Intel has extended the adaptive voltage function with an advanced voltage offset. It is implemented in the ASUS BIOS as VF point offset. VF point offset allows the user to change the default VF curve by offsetting the voltage at specific frequencies on that VF curve. Unfortunately, this function is not enabled on non-K CPUs. On non-K Alder Lake processors, it's impossible to change any point on the voltage frequency curve. So we only have two options. Either we use a fixed CPU voltage, or we make use of the adaptive voltage mode to maintain that dynamic voltage frequency curve. We can make use of offset mode, and by using an offset of 200 mV, we essentially lift up the entire curve by 200 mV. The main challenge is that this lifts up the voltage for any ratio between 8x and all the way up to 44x. For your reference, I've mapped the voltage frequency curve of this Core i5-12400 processor with and without voltage offset. As you can see in this graph, the voltage for 8x has increased from 0.773 volts to 0.968 volts, and the voltage for 44x increased from 1.128 volts to 1.305 volts. We move the entire VF curve when we adjust the BCLK frequency to 120 MHz. Whereas our original offset voltage frequency curve uses 1.305 volts at 4 GHz, the BCLK adjusted curve maps a voltage of about 1.18 volts to 4 GHz. Just for fun, I also include the VF curve of the 12900KF from SkatterBencher number 34. As you can see, the Core i9 requires substantially lower voltage than the Core i5. Upon entering the BIOS, enter the Extreme Tweaker menu. Set AI Overclock Tuner to XMP1. Set BCLK frequency to 120.5. Set ASUS Multicore Enhancement to Enabled Remove All Limits. Set DRAM frequency to DDR5 62-66 MHz. Set Performance Core Ratio to By-Core Usage. Set 1-core and 2-core ratio limit to 44. Set 3-core and 4-core ratio limit to 42. Set 5-core and 6-core ratio limit to 40. Enter the AVX related controls submenu. Set AVX512 to enabled. Leave the AVX related controls submenu. Enter the Digi Plus VRM submenu. Set CPU load line calibration to level 2. Leave the Digi Plus VRM submenu. Enter the internal CPU power management submenu. Set regulate frequency by above threshold to disabled. Leave the internal CPU power management submenu. Enter the Tweaker's Paradise submenu. Set Unlock BCLK OC to enabled. Leave the Tweaker's Paradise submenu. Set max CPU cache ratio to 40. Set CPU core cache voltage to offset mode. Set offset mode sign to plus. Set CPU core voltage offset to 0.2. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Unsurprisingly, thanks to our 900 MHz frequency improvement from 4.4 GHz to 5.3 GHz, we achieved the best performance in single-threaded benchmark applications with up to 32% improvement in Cinebench R23. Our multi-threaded performance is also significantly better than stock as we increased the all-core frequency by 800 MHz from 4 GHz to 4.8 GHz. We see the highest performance increase with 43% in AI benchmark. When running Prime 95 small FFTs with AVX enabled, the average CPU peak core clock is 4802 MHz with 1.216 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 23.5 and 33.8 degrees Celsius. The average CPU package power is 154.5 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU peak core clock is 4802 MHz with 1.196 volts. The average CPU temperature is 84 degrees Celsius. The ambient and water temperature is 23.5 and 33 degrees Celsius. The average CPU package power is 133.5 watts. Alright, let's wrap this up. First, the overclocking results. Obviously, they're spectacular. I was able to get my CPU up to 5.3 GHz for single-threaded applications and up to 4.9 GHz for multi-threaded applications. That's a 900 MHz improvement across the board. Obviously, the performance improvements will be spectacular as well. So we saw up to 44% uplift in AI benchmark. The main constraint for this CPU is the H0 die. It's a much smaller die than the CPUs that have E-cores on board, and therefore it's much more prone to hotspots. So what I saw was that the hotspots were the main thermal constraint for my overclocking results, not the total power consumption. That also means that probably you'd be able to max out a CPU with the H0 die with just a 240 AIO or maybe even a 360 AIO. That should be more than fine. Also, unfortunately, the lack of advanced overclocking tools that are present in Intel's OC mailbox also severely limits our capability to max out the CPU. So in the traditional approach where we use a fixed voltage, here we can't really benefit from the high single-threaded boost. And when we use a modern approach with the dynamic voltage scaling, when you end up with a multi-threaded workload, maybe with even AVX enabled, we don't have access to the AVX offsets to reduce the frequency and lower the temperature. So yeah, not having access to the advanced tools present in K processors is kind of a problem for non-K overclocking, obviously. The bigger story for non-K overclocking is, as I mentioned in my introduction, that there's a lot more to this story than just being very happy that you have BCLK on non-K processors. I think it's important to add more context and color to Alder Lake non-K overclocking than what I've seen from media and the overclocking community so far. Alder Lake non-K overclocking exploits an oversight in a very early pre-release microcode where the BCLK governor does not monitor the external clock generator. So it allows for unmonitored BCLK overclocking. So while that enables overclocking for non-K processors, it doesn't re-enable any of the other restrictions that are imposed on non-K processors. And most importantly, it does not provide us with access to the tools that are available in the Intel OC mailbox. I think Intel has very good reasons to hide these premium overclocking features behind a paywall. First, obviously, there's the financial aspect, but On the other side, I think it makes sense for Intel to charge a price for these premium features and earn money for the value that it creates for overclockers, right? Since its inception in 2013, the OC mailbox has provided overclockers and enthusiasts with an incredible amount of options and an incredible amount of value to help unlock more performance from your K and X CPUs. The premium charged for overclocking features on Alder Lake is about $18 for the Z chipset and between $66 and $100 for a K processor, depending on whether you go with an i5, i7 or i9. That's similar to what it was on Rocket Lake, but significantly higher than Comet Lake, where the premium charged for a K CPU was about $50. Second, also obviously, I think that where we see digital security and the cyber in the news headlines every day, it makes sense for Intel to really try and prevent overclocking on parts that don't officially support it. I don't think it's reasonable to argue that every single CPU should be fully unlocked, though I think it's probably reasonable to argue that maybe there should be more overclockable parts and perhaps those parts should be priced more affordably. At the end of the day, it is up to every one individual to determine whether they're willing to pay the price premium for the value that's created in in overclocking features. While researching this Alder Lake non-K overclocking story, I also gained a lot more appreciation for what the engineers in the Intel OC lab and the engineers in the motherboard R&D teams are doing. On Intel's side, it's clear that there is a dedicated effort to create and further enhance value for enthusiasts and overclockers. Judging by what's come out of the OC mailbox since 2013, it's impossible not to be impressed. On the motherboard side, it's also incredible to see how these R&D teams still relentlessly pursue to find more ways to provide more performance to end users. I think on Alder Lake, both the AVX512 and the non-K finds or enablement is a prime example of that relentless pursuit for more performance. They find an opportunity and then they find ways to bring it to the end user as well. Anyway, that's all for today. This story was obviously a huge piece to compile, so it had me ignore some of my other overclocking platforms for a while. I do have some other exciting videos upcoming, so feel free to subscribe if you're looking for more overclocking content. I want to thank my Patreon supporter, Coffee Pen Bit, for supporting my work. For those who want to have a closer look at my BIOS settings or want to read through my story, I'll also put up a written version of this video on my blog. And that's about it. See you next time.